Hello and Assalamualaikum to our panelists and viewers for my video presentation. This video is purposed to present about my final year project MEC601 with project title of Design of Badminton Shuttlecock Feeder Formation Mold for Injection Molding Machine. My name is Muhammad Fatihin bin Mohani. I will be the presenter of the video. My supervisor is Sir Tajudin Jahi. Let me talk deeply. Project Summary. The project will explain on how the characteristic of the current shuttlecock on the market and what the reason of its low durability and high cost production in terms of design aspect. The project also will compare on the parameter of two types of shuttlecock in current market, which are feather formation shuttlecock and plastic shuttlecock. Moreover, the project is focusing on the parameter for producing feather formation shuttlecock mold for injection molding process, and the method used in the project is by determine the parameter and design the mold by using CAD software, which is SolidWorks. The introduction. For history review, the shuttlecock story starts from 1840, where the feather with velvet covered cork-based design by Bertoldo. Then in 1910, a straight shuttle rounded and feather made in England. Then in 1935, an experimental shuttle using natural gut, but the shuttle is inconsistent in spread and erratic in flight. In 1952, the first plastic shuttle named PL-MAN produced widely by Nakapura Company in Japan. And in 1963, Azhan Company designed a 3 rows of stitching shuttlecock. Anyway, the current design is still using 2 stitching shuttlecock made by several companies such as RSL and Yonex. In overview, feather shuttlecock is made by 16 overlaid duct of ghost feather, where it is laced by thin threads around the shuttlecock and the cock is permanently attached at the end of the head shuttle. The feather is traditionally made where the process needs labor to plug the feather into the shuttle and stabilize the performance itself. The feather is commonly used in tournament until now. For the plastic shuttlecock, or we known as nylon shuttlecock, there are several designs made by different several companies where the material is still using plastic material, but still it's using round-based cork at the end of the shuttle and it is removable. The process of the shuttle is using injection molding, and is, however, the shuttle only suitable for recreational game. There are few efforts made by some companies try to replace feather formation shuttlecock with new artificial shuttlecock. The reasons are to reduce usage of animal product and increase the reliability of shuttlecock itself. For example, in 1982, a patent published to replace the material of feathers from a shuttlecock using woven and non-woven cloth fiber with the same method of process production, which is by using traditional method. For the literature review, there are 3 important points will be explained in literature review, which are design influence towards shuttlecock performance, comparison between process of production, and mold design parameter. The first point is design influence towards shuttlecock performance. As we know, both feather and plastic shuttlecock differ in performance. In trajectory factor, plastic shuttlecock move faster and long in range than feather shuttlecock. The factor could be explained because of porosity of the feather and factor of angle on the design. Based on the relation between drag coefficient and Reynolds number, there are difference in drag coefficient between feather shuttlecock and plastic shuttlecock. In feather shuttlecock, the drag coefficient is constant due to the constant of the Reynolds number. However, in plastic shuttlecock, the drag coefficient decreases due to the increasing the Reynolds number. Thus, low in drag coefficient increasing the trajectory range of shuttlecock. For the factor of angle, there are 3 angles play important role in shuttlecock design, which are angle of skirt, angle of attack, and angle of feather. The symbol can be seen in the picture. To be more clear, skirt angle is angle between a reference line on a body and tip of the feather. It affects the drag coefficient, where the smaller drag coefficient is consequence of smaller angle of skirt. So, the shuttlecock will fly longer and vice versa. Attack of angle. Attack of angle is an angle between reference line on a body and relative wind act on it. The increasing angle of attack will cause increasing of drag coefficient. For the angle of feathers is an individual angle of formation of the feathers. Increasing angle of feathers will increase the overall gap between the feather formation. Thus, the drag coefficient also increase. All these three angles directly proportional in relation with drag of coefficient. The next point for literature review is comparison between process of production. There are three processes compared for this project to select which one is suitable for artificial shuttlecock production, which are additive manufacturing, compression molding, and injection molding. The first process is additive manufacturing. Additive manufacturing, or known as 3D printing by public, is a rapid prototyping process where it could produce the product in a fast pace with great complexity shape. The process generally known to produce the part layer upon layer designed from 3D model data in CAD. The process usually implemented in automobile, aerospace, and biomedical industries. The next process is compression molding. The process of compression molding is the material preheated in an open place. Then, the mold cavity heated and closed with high pressure applied into contact of mold areas. Thus, the part produced following the mold design. It is similar to injection molding. The difference is there is no gate at the compression molding. The advantage of process is no mark defect because there are no gate on it, and the maintenance is low, and the waste produced also low. However, the design availability in the process is less complex compared than in injection molding. The next process is injection molding. This process of making part by injection molten material into a mold. As seen in the figure, the additive and resin fed into the hopper then through the heating phase, where the additive and resin mix amount. Then, the hot molten material injected to the cavity through the runner. This phase is called filling phase. Then, the mold is through the cooling phase until it becomes rigid to be ejected. The mold is then ejected and then process start the new cycle. Injection molding highly used as it cools them with great complexity design and excellent tolerant control. For the artificial shuttlecock production, injection molding chosen as its advantage in high design complexity and issued in lead time. The process is turned down because long in lead time, but it's not suitable for mass production. The next point is mold design parameter. The mold design parameter is important to ensure the mold design accurate without any defect. The variables need to be considered are mold size, cavity count, cavity layout, runner system, gating system, venting system, and ejection system. Each of these variables is important to ensure the design parameter both shuttlecock and mold can be merged. Next, the scope and limitation. The scope of limitation of this project are the process only focusing on design approach. The other parameters such as material or aerodynamic are not deeply discussed. Then, the process of designing only use SolidWorks as main software to making both shuttlecock and mold design. The problem statement of this project is, since the process of making feather formation of shuttlecock is high, and the feather shuttlecock is less durable by using feather material, the production of the shuttlecock should be changed to a better process by using injection molding and different material. To be more clear, the research question could be divided into three. First, is artificial shuttlecock capable be produced as mold in injection molding process? Second, could the mold design with low complexity? Third, what is the constant parameter should be taken while designing the mold? Then, the question could be solved by following this objective. First is to identify the new artificial badminton shuttlecock with the formation mold for injection molding machine. Second is to develop the simplest shuttlecock mold design. And the third one is to investigate the parameter affect the feather formation mold process. The methodology for this project is following the chart shown. The chart covers both FYP1 and FYP2, where it starts with data gathering from relating journal and identify the problem and its expected result by refer the previous journal. Then, design the feather formation shuttlecock following the standard dimension of Yonex Aerosol 40. The chosen of Yonex Aerosol 40 because it's approved by BWF. Then, design the mold using SolidWorks. Then, Identify the parameter and geometry for the mold. If the parameter and geometry not suitable for the mold, the shuttlecock design should be modified. If the parameter and geometry is suitable, then discussion process taken place, and the conclusion and then end of the project. The expected result. By referring the previous fundamental related research study, there are 5 design requirements expected between the shuttlecock and the mold design expected be parameters of artificial shuttlecock mold development. The first one is the dimension and its tolerance. The dimension of the design shuttlecock is as follows. It will be the reference for the mold making where all shape copied from this dimension. If there are any errors such as irrelevant rough angle, the shuttlecock design will be adjusted. The tolerance will be considered while making these two parts, which are shuttlecock part and the mold part. The next one is requirement skirt angle on shuttlecock shape and mold design. As discussed in literature review, there are 3 angle factors considered in mold making. By following the standard shuttlecock angle, the angle of skirt will be expected be 20 degree, angle of feather is 10 degree, and angle of attack will be 0 degree. The next one is the surface design. As stated in the literature review, the porosity of the surface design might be give little effect, but in this project, the porosity is expected to be neglected because the complexity in process to get the perfect porosity surface. Next, venting design is following part shape. Generally, the venting groove expected to be cut at the last area of the mold to fill because the area usually traps more air and causing a gas burn on the part. In this case of shuttlecock, the vent may be grooved in every tips of the feather. The next one is head plug and runner system. The body of the plug connected to the form by plugging. The plugging part expected will be connected to the runner, gear and screw. Next, figure shown on how the expected process will be done. As stated in methodology chart, the process is expected starting with measure the dimension of the shuttlecock, then visualize it into CAD model in SolidWorks, then modify it with headless shuttlecock design, and then determine the parameter to make it fit into injection molding mold parameter. So that's all my presentation on final year project 1. Thank you.